The first type of number patterns is arithmetic sequence. A common difference is the primary feature of such progression. Learn about it here in Mathematics of Engineering. Arithmetic sequence or progression is a number pattern connected by either adding or subtracting a constant value, which is called common difference. For the pattern 3, 6, 9, 12, 15, and 18, the numbers keep going by addition of 3. For the second progression, starting from 100, the succeeding terms are determined by subtracting 5. With the different types of sequences, how can we identify arithmetic sequence? It is determined by knowing the common difference. So for the following patterns, let's determine if they are arithmetic sequences. Take the first pattern. From 35, the succeeding term is 32 because of subtracting 3. And then 32 jumped to 29 by again subtracting 3. And lastly, we got 26 by another subtraction of 3. Having a common difference of minus 3, the pattern is an arithmetic sequence. For the second pattern, we take negative 64 minus negative 34 to get a difference of negative 30. And just the same, negative 94 minus negative 64 is negative 30. And again, negative 124 minus negative 94 yields negative 30. Negative 30 is constant and we term it the common difference, so the pattern is an arithmetic sequence. The third pattern shows an increase of 5 from 9 to 14, and also plus 5 from 14 to 19, and still the same from 19 to 24. The constant increase of 5 is the common difference. Thus, the pattern is another arithmetic sequence. The last pattern starts with 10, followed by 20, so there is a difference of positive 10. Then 40 minus 20 gives positive 20. And again, 80 minus 40 gives positive 40. Having variable differences, the pattern is tagged as not an arithmetic sequence. The explicit formula of arithmetic sequence is a sub n is equal to a sub 1 plus d times the quantity of n minus 1, where a sub n is the nth term, or the term we are considering. A sub 1 is the initial term. D is a common difference, and remember that these should be constant all throughout the sequence, and n is the number of terms. Let's work on the first example, where we are asked to find the 10th term of the pattern 4, 10, 16, and so on. From the statement itself, we know that the number of terms to consider is 10, and the initial term is valued at 4. What we are looking for is a sub n, which is a sub 10. From the pattern, we can compute for the difference and check if it is indeed constant by having 10 minus 4, which is 6, and again verify it with 16 minus 10, which is again 6. So the common difference is positive 6. Having all these values known, we use the explicit formula to solve for the required, that is a sub 10 is equal to 4 plus 6 times the quantity of 10 less 1. Simplify the numbers enclosed in the parentheses as 9. So we get 4 plus 54, or that is 58. The next example is to determine the 11th term in the fractional arithmetic sequence. So knowing the given parameters of number of terms, which is 11, the initial term as 5/4, and we are tasked to determine a sub 11. Identify the difference using the pattern, which is 19 all over 8 minus 5/4, and that is equal to 9/8. Verify with the other terms. So 7/2 minus 19 all over 8 is also 9/8. Again, 37 all over 8 minus 7/2 is also 9/8. And 23 all over 4 minus 37 all over 8 is 9/8. Thus, the common difference is positive 9/8. From the explicit formula, we can now plug in the values to have a sub 11 is equal to 5/4 plus 9/8 multiplied by 11 less 1. Simplify those in parentheses as 10, and do the operation to have a11 is equal to 25/2. The next problem asks for the term of negative 81 in the arithmetic sequence 27, 24, 21, and so on. The initial term of the pattern is 27, and the final term is negative 81. We are only to determine n. Again, look for the constant difference from the pattern itself. So 24 minus 27 is negative 3, and 21 less 24 is negative 3. The common difference in the pattern is negative 3, and this is what we place in the formula. So we have negative 81 is equal to 27 plus negative 3 multiplied by n minus 1. We eliminate the parentheses by distributing negative 3 and get negative 81 is equal to 27 minus 3n plus 3. Collect all constants and have negative 81 is equal to 30 minus 3n. Then, transpose 30 to the other side of the equation to have negative 111 is equal to negative 3n. Finally, we can isolate n by dividing everything by negative 3 to get n is equal to 37. Example 4 states, check whether negative 150 is a term of the arithmetic sequence 11, 8, 5, 2, and so on. Start with the given parameters, like a sub 1 is 11, and a sub n is negative 150. We are looking for n. From the pattern, we can compute the difference starting with 8, take away 11 is negative 3. 5 minus 8 is negative 3, and 2 less 5 is negative 3. The common difference is negative 3. Using the explicit formula, we place negative 150 is equal to 11 plus negative 3 multiplied by the quantity n minus 1. Distribute terms with parentheses to have negative 150 is equal to 11 minus 3n plus 3. Collect all constants to have negative 150 is equal to 14 minus 3n. Then, transpose 14 to the other side to get negative 164 is equal to negative 3n. Isolate n by dividing both sides by negative 3, resulting to n equal to 164 all over 3. Having the number of term as a fraction implies that negative 150 is not a term in the pattern. Moving on to the next level. If the second and eighth terms of an arithmetic sequence are 6 and negative 6, then which term of the sequence is 0? Identify the given parameters, like a2 is 6 and a8 is negative 6. A sub n is 0, and we are tasked to look for n. With the lack of pattern, we are unable to solve for the common difference, which accounts to n and d as missing parameters in the problem. However, by using the explicit formula, we equate a2 as equal to a sub 1 plus d multiplied by the quantity of 2 minus 1. A sub 2 being 6, and simplifying the quantity gives 6 is equal to a sub 1 plus d times 1, or that is 6 is equal to a sub 1 plus d. Let's treat this as equation 1. Do the same with a8. So we have negative 6 is equal to a sub 1 plus d multiplied by 8 minus 1. So if we simplify the quantity to have 7, the equation turns out as negative 6 is equal to a sub 1 plus 7d. Take this as equation 2. With a1 and d as unknowns and having two equations, we can solve them simultaneously. We subtract equation 2 from equation 1, or that is 6 is equal to a1 plus d minus the second equation, negative 6 equal to a1 plus 7d. And we eliminate a1, getting 12 is equal to negative 6d. By dividing everything with negative 6, d is solved as negative 2. Knowing d, we plug it in equation 1, which is 6 is equal to a1 plus d. So we get 6 is equal to a1 plus negative 2, and a1 is determined as 8. So with the requirement of identifying which term is equal to 0, we use the values in the explicit formula. So we have 0 is equal to 8 plus negative 2 multiplied by the quantity n minus 1. Distribute terms to have 0 is equal to 8 minus 2n plus 2. Collect constants to get 0 is equal to 10 minus 2n, then transpose negative 2n to the other side, giving 2n is equal to 10. Then divide them by 2 to have n equal to 5. So 0 is the fifth term of the sequence.